Hi everyone. In this video, we are going to prove the transitivity of the action of the automorphism group of f over e on the prime divisors that lie above a particular prime divisor of e. Okay, so this is the theorem we are set out to prove. We have an f over l, a finite normal function field extension of e over k, and p, small p, is a prime divisor at the bottom level of the function field, the lower function field. So what we're saying is that the automorphism group of f over e acts transitively on the set of prime divisors lying above small p. So in other words, if you take any two prime divisors, capital P and capital P prime of f over L, both of which lie over P, then you can always find an automorphism, sigma, of f over E that maps a capital P to capital P prime. Okay, that's what transitivity means. And if we are going to go back for a second, that we did last time, I need to remind you something about Galois theory, which you know, and if you don't know, I talked about it in the videos, like recap videos. I think it was 8.5 in the numbering that I have on YouTube. So say f over L is a normal, as in our case, finite extension of e over k. So we are going to denote by E sub s the maximal separable extension of E in f. Right, so recall that if you have a finite normal extension, it's more generally, but in particular in that setting, you can ask yourself, what are these elements in F that are separable over E? And so that will be some subset of F that contains E, because of course every element in E is separable over E. Its minimal polynomial is x minus that element. And it turns out that this is a field, a subfield of F. So if you have, well, we know that if you have two separable elements, then their sum is also separable, and certainly it's an F, and it's also a product and so forth. And and we know more of that. More than that, we know that the extension we know that the extension ES over E is separable. It's kind of the maximal separable extension of F over E, so it's obviously separable. So it's also normal. This extension ES over E is also normal. I mean, recall that if you have a normal extension and you consider a subfield, then automatically this is going to be normal. But not that. Typically that's not normal when this is normal. But in our case, because of the specific choice of field here, we have that this thing is a separable extension and is normal, and so it's a Galois extension. So that's the usual way in which you cook up a Galois extension from a normal extension. Everything is finite here. And right, so usually what happens is that you kind of study this extension and then infer about that one. And indeed, the extension of f over es is also very simple, not simple in the algebraic sense, but simple. Because what you can show is that f over es is what's called purely inseparable. Right, so separable means that so an element is separable if its minimal polynomial over the ground field has no repeated roots, and purely inseparable means that the minimal polynomial has only u as its root. Okay, so what I'm saying is that every element x in F, it's too bold, there is some power of it that takes that element to ES. And that power is going to be also a power of the characteristics. And in fact, there is one power that actually, because of the finiteness, that takes all of the elements in F into ES. Okay, so there is some Q like that every element here to the power Q goes down here. I mean, maybe there is a smaller power that does that, but definitely Q. And that Q is exactly going to be the extension of this degree, the degree of this extension. So what's written here? And we also denote this number as the index of f over e, but with this little I, which reflects the fact that we care about the inseparable extension degree. Okay, so to recap, this is always a Galois extension because f over e is normal, and the automorphism group of that is actually that's a Galois extension. So right, every automorphism of ES over E maps ES to itself, and actually because of that fact that every element here in F to the power Q actually sits in ES, if you think about it, it actually means that there is only one way to extend any sigma in the Galois extension here to an automorphism of F over E. And so this means that the Galois extension of ES over E is the same as the automorphism group of F over E, in the sense that, given an automorphism of F over E, you can always restrict it to E sub S, and you get an element in this Galois group of S over E. And on the other hand, if you start with an element in this Galois group, then there's a unique way of extending it to an automorphism of F over E, so I think of them as the same, okay? Even though technically its domain is smaller. And I leave it to you as an exercise to prove that because of what I said, that this is indeed there is a unique way of doing it. Okay, so that's the Galois you need to know. And again, I talked more about it in the previous videos if you want to recap or look at Richard Borcherdt's amazing videos and so forth. But let's continue on. So what I want to do here, and again, I'm slide before the proof of the theorem in the statement, but I need this. So let's consider the following thing. So let's say you take an element Z in E sub S, right? E sub S is the maximal separable extension of F over E. So you take something here, okay? Then let's ask ourselves what happens. So G is again the Galois group of this Galois extension. So you have this group G sitting like parallel to that in a sense. And let's ask ourselves what happens if you take an element sigma in G, apply sigma to Z, so it looks like this, rather than like that or something, and take the product, right? So you apply, you let sigma act on Z of all sigmas, and you take the product. Right, I mean, every sigma Z is also in ES because this is a Galois extension, so it's normal. And what I claim is that this element, which is the product of these elements in ES, actually is actually in E. And the reason is that it is fixed by all elements of G, right? And okay, so why is that? Because if you take a tau and you apply it to this product, like that, you apply tau to this product of element in ES, right, when tau of a product, tau of AB is tau of A, tau of B, so you can take the tau apply to the products to the product of taus apply to sigma Z like that, but that's the same as doing this, of course, because of the rules of group actions. And then you can see that here and here you actually do the same. You multiply over all elements in G and apply them to Z, but you do it in a different order. So here you go according to the, whatever order you have in mind in G, and here you do a shift by tau. But you're still going over all elements in the group, so you get the same element. Right, so this element is fixed by all elements in G, in the Galois group of ES over E. And so this means that this element is in the fixed field of ES over G, ESG, in the fixed field of ES by G, but that's E, right? Because this extension is Galois, then we know that an element is being fixed by an element in the field is fixed by all elements in the group precisely when it is in the lower field, E. Right, so what we just said is that this element actually lives in E. Okay. Now, I want to talk about F rather than ES. So let's take X in F. And when we know that X to the Q, or Q, which is the degree of this extension, is in ES. And so this means that I can take my Z from before to be X to the Q, right? Because, whatever X is in F, X to the Q is some Z in ES. So I know that also this thing is in E. And this leads us to define the notion of a norm of finite normal extensions. I think Tomer talked about it slightly, but not in that generality. So the norm of a normal extension, finite normal extension, you need finite because you need a Galois group to be finite, otherwise you can't multiply all of those things. But you don't need separability, just normality. So a finite normal extension has a norm, and the norm, denoted like that, applied to X, is, let me do one more step before here, is, well, it's this thing. Right, it's like kind of hiding what's written. It's this thing. Okay, so you take your element X, you pull it down to ES by taking its cube power, and then you apply every sigma in G, take the product, you get an element in E. That's the norm. It's a function from F to E. Now here I did a slight transition, which is kind of okay, but not quite. So it's fine, but I need to say something about it. So of course, we know that sigma of x to the q is sigma of x to the q. And so sigma of x to the q is sigma of x to the q. And definitely, you know, sigma is multiplicative, so you can push this product as I did here, and then everything, and also through the power q, and everything's fine. However, the only point to note is that sigma is defined technically on ES, right? It's an element in the Galois group of ES over E, so I can write sigma to the x to the q without justifying anything because x to the q is in ES. But when I write sigma to the x, like already here actually, I'm kind of, I mean, technically I cannot do that because sigma wants to eat something from ES, not from F. But as I said, there is a unique way of extending sigma in G, in the Galois group of ES over E, to sigma in the automorphism group of F over E. And so there is only one way of understanding this, and so it is okay to write sigma of something in F with the understanding that I mean, you know, the unique extension of the sigma that's defined in ES, on ES. Okay, so with that, I can just say that the norm is defined like that, and that's a map from F to E. Okay. Okay, so with this, actually, the proof is not so difficult. So let's assume by contradiction that there is some p in p prime and capital P and capital P prime, such that capital P prime is not sigma p for any sigma in the automorphism group of F over E. Okay, I mean that's the contradiction to this transitivity. Then if you think about it, it means that the orbit of P, capital P prime and capital P are disjoint. Right? I mean, you can't, there is no way for these two sets are disjoint. Because if they weren't disjoint, then you had like sigma 1 P prime equals sigma 2 P, and therefore, you could have written P prime as sigma 1 inverse sigma 2P. You kind of assume that you can't do that. Okay, so by this contradicting assumption, we know that we have these two disjoint orbits. And now the point is we are going to look at these two orbits at the level of E, because there they kind of agree. All of them lie above little p. So what we are going to do is we are going to use the weak approximation theorem to find an X, an element in the field, the big field F, such that for every sigma in G, I will require, V sigma, a capital P of X to be positive. So elements from here are positive, and elements from here are negative. So V sigma of P prime X is negative. I mean, and I can do that, right? Because these are disjoint sets. So there are no conflicting requirements here. There are only finitely many requirements because to begin with, the Galois group is finite because the extension is finite. You can definitely do that. Note that there are like maybe repeated requirements here because maybe, like for example, if sigma stabilizes P and also the identity does that, then you get the same requirement multiple times, but that's okay. Just take the representatives of the requirements if you. Okay, so let's say we found such an X. And now I kind of want to see what happens to this X in E. And because of that, I define the norm. I mean, we will need the norm later on also, but only also for that particular reason. So we call that Y, which is the norm of f over E applied to X. I mean, I'm defining Y to be the norm of applied to X. This thing is this expression that we have just defined before, and it's an element in E, right? Because the norm of f over E is always an element in E. So now let's consider the norm of the valuation, the capital P valuation of Y. Okay, so the capital P valuation of Y, well, I mean, it's the valuation of this thing. So, okay, so the valuation of that is Q times the valuation of their product, which is actually Q times the sum of the valuations of the individual terms. So this is Q times the sum over all sigma in G of the valuation applied to that individual term. And of course, this whole thing happens in Z, right? You see a Q, you may think the characteristic makes it vanish, but this is a calculation in Z, right? This is a calculation in the image of the group, in the group, all the group that we have, the image of the valuation. Anyhow, so you have this, and you can also write it like that, right? V capital P of sigma X is just V sigma inverse capital P of sigma inverse sigma X, which is X, right? It's the same thing. And that's kind of how we define the sigma of a prime divisor. And the reason I want to write it like that is because I want to see an X here, okay? Because of the way I kind of had the requirement from the weak approximation theorem. But anyhow, if you go over all sigma in G and do this, then it's the same thing as going over all sigma in G and do sigma capital P. Right? Because this is just, you move around the orbit of capital P one way or another. And this is, of course, positive, strictly positive, because we required X to be such that this, V sigma P of X to be positive whenever you are in this set, for all sigma P's. So this is a positive number. And because Y is in E, we can actually also figure out that Y's valuation as an element in E is positive, right? So V of small p of Y, which differs from that only by the ramification index, which is non-negative, it's at least one, is also positive, right? You just divide this number by some integer, positive integer. And okay, so you got on one hand that the valuation, the small p valuation of Y is positive. But on the other hand, you can do the entire calculation with the primes here. Right? So you just have to put primes everywhere. Here and here and here and here. And then what will happen is that you'll again figure out that V small p of Y is this thing. There's a prime here and a prime here, but now everything is negative, which is a contradiction to the fact that in a second ago it was positive. Yeah, so that's the proof for the transitivity of the automorphism group of f over E acting on a prime divisor lying over a particular divisor, prime divisor in E. Okay. So next up, we are going to talk about, in the next videos, two important groups, the decomposition group and the inertia group, and prove some interesting equalities. In a sense, these groups kind of explain what is E and what is F using structure, not just a number or like index of some group. It's going to be sizes and stuff of these groups. Okay, you'll see.